Astronomers studying data from the James Webb Space Telescope found something on the surface of Pluto that does not match any known chemical compound in their entire database. Not a rare mineral, not an unusual form of ice, something that, when compared against every existing model of what should be there, simply does not fit. And when researchers checked whether the same mysterious signal existed anywhere else in the solar system, they found it in exactly one other place, a moon orbiting Saturn nearly 1 billion miles away. We are talking about a genuinely unresolved chemical mystery discovered on Pluto using the James Webb Space Telescope, one that connects our solar system's most famous dwarf planet to Titan, Saturn's largest and strangest moon. If you think you already know everything there is to know about Pluto from the New Horizons flyby back in 2015, stick around, because this particular discovery has left researchers using a phrase you do not often hear from professional scientists, admitting flatly that they cannot say what it actually is. Let's start with some quick background, because understanding how researchers even found this signal in the first place matters enormously. Since the James Webb Space Telescope launched in December of 2021, it has repeatedly turned its instruments toward Pluto and its largest moon, Charon, taking advantage of infrared observation capabilities that simply did not exist during earlier missions to the outer solar system. Much of this research has focused on a technique called spectroscopy, splitting incoming light into its individual wavelength components to identify the unique chemical fingerprint left behind by different molecules and compounds. Because virtually every chemical substance absorbs and reflects light in its own distinctive pattern, astronomers can use this method to identify materials on distant worlds without ever needing to physically visit them. Using this exact technique, researchers studying Pluto's surface identified an unusual, unexplained absorption signal centered at a wavelength of 5.113 micrometers, a very specific point in the infrared spectrum. When scientists compared this signal against detailed radiative transfer models, computer simulations, incorporating every known gas and haze particle present in Pluto's atmosphere, the absorption simply did not appear anywhere in their simulations. According to the research team, the signal did not resemble typical atmospheric absorption at all, and its shape ruled out the possibility that it was simply leftover methane absorption being misread as something new. Before we go further, if genuine, still unsolved scientific mysteries are exactly the kind of thing that keeps you watching, go ahead and tap that like button right now. It really does help this channel keep making videos exactly like this one. Here is where the story gets even stranger. This exact same unexplained signal was independently detected on Titan, Saturn's largest moon, an object separated from Pluto by roughly 1 billion miles of empty space, with an entirely different atmospheric composition, and an entirely different set of environmental conditions. Researcher Benoit Bizarre first noticed this unusual feature while analyzing Titan observations gathered by Webb back in November of 2022, when the telescope managed to detect infrared light leaking through Titan's notoriously thick, hazy atmosphere in a very specific, narrow band of wavelengths, allowing scientists a rare glimpse directly through to the moon's surface below. Titan presents an especially difficult challenge for this kind of surface study, since its atmosphere is extraordinarily dense, with surface pressure roughly 50 times greater than what we experience here on Earth. Sunlight, attempting to reach Titan's surface, has to pass through multiple thick layers of gas and haze particles that absorb and scatter light along the way, making the moon's actual surface chemistry notoriously difficult to study directly. Researchers specifically took advantage of a narrow atmospheric window between 4.9 and 5.4 micrometers, a range less affected by haze interference than most other wavelengths, giving them one of their clearest looks yet at light actually reflecting directly off Titan's surface, rather than simply bouncing around within its thick atmosphere. If you are new here and enjoy watching real scientific mysteries unfold without a neat, tidy resolution handed to you immediately, now would be a great time to hit that subscribe button, because there is a lot more of this waiting for you. When the same signal turned up on Pluto as well, appearing at the same specific wavelength on two completely different, physically separated worlds, it transformed what might have looked like a simple instrument quirk or measurement error into something researchers had to take far more seriously. Finding an identical, unexplained chemical signature in two independent locations makes it significantly less likely that the signal represents some kind of calibration mistake or data processing artifact, and significantly more likely that it reflects a genuine shared chemical process happening on both worlds. That raises the obvious question everyone studying this data wants answered. What is actually causing it? Researchers have proposed a few candidate explanations, though none of them have been confirmed. One leading possibility involves complex organic molecules, compounds built primarily from carbon and hydrogen atoms, potentially forming through chemical reactions triggered by sunlight interacting with simpler molecules like methane, similar to the kind of chemistry already known to produce Pluto's distinctive haze layers. Both Pluto and Titan share broadly similar base ingredients in their atmospheres, nitrogen and methane, undergoing photochemical reactions driven by sunlight, which could plausibly produce shared, more complex byproducts on both worlds, even though their environments differ significantly in temperature, pressure, and overall atmospheric density. However, researchers have been careful to emphasize that this remains a genuine open question, rather than a settled conclusion. The specific molecule responsible for this signal has not been definitively identified, and researchers involved in studying it have been refreshingly honest about the current limits of their understanding, stating plainly that they simply cannot say for certain what the substance actually is at this point. That kind of candid uncertainty is rare enough in science communication that it is worth highlighting on its own. A reminder that even with humanity's most advanced space telescope pointed directly at these worlds, some genuine mysteries remain stubbornly unresolved. This mystery signal adds to a growing, genuinely fascinating picture of what Pluto's atmosphere and climate system actually look like, one that has been rapidly filled in by James Webb's observations over the past few years. Earlier research, led by planetary scientist Si Zhang at UC Santa Cruz, confirmed a theory first proposed back in 2017, suggesting that Pluto's high-altitude haze, a bluish, multi-layered blanket, stretching more than 185 miles above the dwarf planet's surface, actively controls its climate by absorbing sunlight during the day and releasing that energy back into space as infrared radiation at night. This haze-driven cooling effect helps explain why Pluto's upper atmosphere runs about 30 degrees colder than models, without the haze would otherwise predict, a genuinely unique climate mechanism that, according to researchers, appears completely different from how any other atmosphere in our solar system actually functions. That same haze also appears directly connected to another strange phenomenon. Webb has helped researchers better understand the way Pluto's atmosphere continuously leaks into space, with some of that escaping material eventually landing on the surface of Charon, Pluto's unusually large companion moon. This ongoing transfer of material from planet to moon, something researchers describe as unlike anything else observed elsewhere in the solar system, helps explain the distinctive reddish tint found on Charon's polar regions, caused by methane molecules escaping Pluto's atmosphere and then undergoing further chemical transformation once they settle onto Charon's icy surface. Taken together, these discoveries paint a picture of Pluto as a far more chemically active, far more dynamic world than its reputation as a frozen, distant afterthought would suggest. This is a place with an actively functioning climate system, unique among every other world we have studied, continuously exchanging material with its own moon, and now apparently home to at least one unidentified chemical compound, connecting it to a completely different moon orbiting an entirely different planet nearly 1 billion miles away. It also helps to understand exactly why this particular wavelength, 5/113 micrometers, matters so much scientifically, rather than simply being an arbitrary number buried in a technical paper. Every wavelength within the infrared spectrum corresponds to specific types of molecular vibrations, the tiny, characteristic ways different chemical bonds stretch, bend, and twist when they absorb energy from incoming light. Scientists have spent decades building enormous reference libraries, cataloging exactly which wavelengths correspond to which known molecules, essentially creating a kind of chemical fingerprint database that researchers can compare newly detected signals against. When a signal like this one shows up at a specific wavelength but does not match any entry in that extensive reference library, it immediately tells researchers they are looking at either an extremely rare, poorly studied compound, or potentially something that has never been properly characterized in a laboratory setting at all. That distinction matters enormously for how researchers approach solving a mystery like this one. In many cases, unidentified signals in astronomical data eventually turn out to be already known compounds that scientists simply had not yet built accurate enough reference models for, particularly for complex organic molecules that can exist in many slightly different structural variations, each producing a subtly different spectral signature. Other times, genuinely novel compounds get identified for the first time, specifically because of exactly this kind of anomalous detection, forcing chemists back on Earth to synthesize and study new candidate molecules in laboratory conditions, specifically designed to recreate the extreme cold and low pressure environments found on distant worlds like Pluto and Titan. This process of matching space-based detections to laboratory chemistry represents one of the more fascinating, lesser-known aspects of modern planetary science. Researchers frequently work in close collaboration with chemists who specialize in recreating the kind of extreme exotic conditions found on distant moons and dwarf planets, conditions involving temperatures hundreds of degrees below anything found naturally on Earth, combined with dramatically different atmospheric pressures and chemical starting ingredients. By synthesizing candidate compounds under these carefully controlled laboratory conditions, and then measuring their own infrared absorption signatures, Scientists can systematically test different hypotheses against the real, unexplained data captured by Webb, gradually narrowing down the list of plausible explanations, one laboratory experiment at a time. It is also worth considering just how significant it would be if this mystery signal eventually turns out to represent an entirely new class of organic molecule never previously cataloged. Complex organic chemistry occurring naturally on distant, icy worlds carries real significance for scientists studying the broader question of how life's basic chemical building blocks might form under a wide range of different planetary conditions. While nobody involved in this research is suggesting Pluto or Titan currently harbor life, studying exactly how sunlight-driven chemistry builds increasingly complex organic molecules on these cold, distant worlds offers valuable insight into the kinds of chemical processes that may have played a role in similar environments elsewhere in the universe, including potentially on other icy moons and distant exoplanets that share broadly similar atmospheric ingredients. Researchers studying both Pluto and Titan expect additional Webb observations to eventually help narrow down exactly what this mystery molecule actually is, potentially by capturing higher resolution spectra or observing the signal under different lighting and seasonal conditions on both worlds. Until then, this remains a genuinely open scientific question, one small but persistent puzzle. Peace in humanity's still developing understanding of how chemistry behaves on cold, distant worlds, sitting at the far edges of what our solar system has to offer. It is also worth situating this discovery within the broader arc of how our understanding of Pluto has evolved over just the past decade. Before NASA's New Horizons spacecraft conducted its historic flyby in July of 2015, most scientific understanding of Pluto came from blurry, low-resolution telescope images, leaving the dwarf planet as little more than a distant, mysterious dot for most of the 20th century. New Horizons transformed that picture almost overnight, revealing a complex, geologically active world with mountains, glaciers, and a surprisingly rich atmosphere, discoveries that upended decades of assumptions about what a small, distant world like Pluto should actually look like up close. James Webb's more recent observations represent the next major chapter in that same ongoing story, adding an entirely new layer of chemical and atmospheric detail that no flyby mission, however successful, could have possibly captured during its brief, one-time pass through the system. That layered progression, a dramatic flyby followed by years of increasingly detailed remote study, reflects how planetary science often actually works in practice. A single mission rarely answers every possible question about a distant world. Instead, each new tool and technique builds upon what came before it, gradually assembling an increasingly complete picture over years, or even decades of sustained scientific attention. Pluto's story did not end when New Horizons sped past it and continued deeper into the Kuiper Belt. If anything, that flyby simply opened the door to the kind of detailed, ongoing atmospheric and chemical study that Webb has now made possible, revealing mysteries that nobody could have properly investigated using New Horizons instruments alone. There has also been growing scientific interest in eventually sending a dedicated orbital mission back to Pluto, one capable of studying these same phenomena over an extended period rather than during a single brief flyby. Researchers have specifically pointed to mysteries like this unidentified chemical signature as exactly the kind of open question a longer term dedicated mission could help resolve, potentially even including instruments capable of directly sampling atmospheric or surface material, rather than relying entirely on remote spectroscopic analysis conducted from millions of miles away. Even about worlds we have already sent spacecraft to visit directly, make sure you are subscribed with notifications turned on, because James Webb continues studying both Pluto and Titan. And there is a very good chance the next round of observations finally identifies exactly what this strange shared chemical signature actually is. Until that moment arrives, this mystery molecule remains one of the more quietly compelling open questions in modern planetary science. A genuine unknown hiding in plain sight on two of the most thoroughly studied worlds in our entire solar system, waiting patiently for the right observation or the right laboratory experiment to finally give it a name.